Hi everyone. Today we are kicking off our trigonometry chapter, and the first lesson in this chapter has to do with arc length and sector area inside of a circle. And you learned how to find both of these things probably back in geometry, but I think you probably learned them before you had learned about the unit circle and how to measure in radians and those kinds of things. So we're kind of taking a different spin at it, and going to be talking more in generalities instead of just me telling you to memorize a specific formula. In fact, I'm going to encourage you not to focus too much on memorizing formulas here and try to think big picture. So first, let's back up and define what a radian is, because a radian is another way to measure angles. The flip side of radians would be degrees. We already know how to measure in degrees. Now we're working in radians as well. And radians are measured by taking a fraction of the circumference of, and I'm actually going to fix this definition here. It's not the fraction of the circumference of any circle. That would be an arc length. It's specifically a fraction of the circumference of the unit circle, meaning with a radius of 1. So, and I don't know that you need to write this down necessarily, but for example, the circumference of the unit circle, well, the circumference of any circle is 2 times pi times radius. If I'm on the unit circle, we would put a 1 in for the radius, and then my circumference would just be 2 pi. That's why we say when we go all the way around the circle in radians that it's equivalent to 2 pi. Okay, this is 1 full revolution. Would be 2 pi in terms of radians. That's going to be important later on too. So just to define these words real quick, arc length and sector area, and I'm not going to write out definitions, I'm just going to draw pictures here, but if you're working in a circle, a sector is when you kind of take a pie piece out of this circle. So that wedge right there would be called a sector. And so the area of that sector, or that, pizza slice or whatever you want to call it, is a fraction of the area of the whole circle. So what we're going to focus on is finding the area of the whole circle and then figuring out what fraction of the circle that pie piece represents. The other term here is the arc length, and the arc length is this length along the outside. So this thing right here is called an arc. And again, that can be measured as a fraction of the circumference of the circle. So if I know the distance all the way around the circle, I could apply that same fraction to the circumference and say, okay, it's this much of the circumference, so this would be the length. Both of those fractions have to do with whatever this angle measurement is. Okay, so I'm going to mark this with theta, and that angle is referred to as a central angle. And so that central angle is what defines that fraction for us. If we're talking in degrees, there's 360 degrees in the circle, so the fraction would be theta out of 360. Okay, if we're talking in radians, 1 full revolution, or the entire circle, is equivalent to 2 pi, so we would say theta out of 2 pi. That's going to become really important down here when we start talking formulas. Okay, so what I'm going to do here is I'm going to really talk in generalities, and really I just explained everything that I needed to. I'm just going to write it down for you, and then we're going to formalize that into some actual formulas down here. But I think knowing this, why this works the way it does, is more important than even knowing just the formulas themselves, because memorized formulas you're going to forget. But if you understand how those formulas are developed, you can come up with them on your own later on. Okay, so for arc length, like I said, measuring this arc is always a fraction of the circumference of the circle. So it's always going to be theta divided by the whole circle, and I'm writing it that way for a reason. Okay, that's the fraction, and then times the circumference, which, remember, circumference is 2 times pi times the radius. I didn't label my radius up here. I think you guys know what a radius is, but I guess I should. Radius is this length right here. Okay. Sector area works the same way. We're going to work with the same fraction, theta, the angle out of the whole circle, times, except now we're talking about area of the circle, which would be measured as pi r squared. So what I have written in blue right there is really the important thing to know. And I don't think that's going to require much memorization if you understand where it comes from, that this is a fraction of the circumference and a fraction of the area. Now, here's something that we can do. So first of all, when I say the whole circle, I'm going to just make a note of this over here. The whole circle is 360 if we're talking degrees, or 2 pi if we're talking radians. And I'm going to flip these back and forth on you. So sometimes we're going to be talking degrees, sometimes we're going to be talking radians. Whatever this angle is being measured in, that's how you're going to decide what's going on the bottom of this fraction. Okay? When I plug a 2 pi in here, okay, so if I'm working with arc length and I'm working in radians, I want you to watch what happens here. Actually, I'm going to do this down here. I don't know that you need to write this down because we're going to formalize it down here in the table, but watch what I'm doing here. If the whole circle is 2 pi, and then I multiply by 2 times pi times the radius, this fraction, with this being on the bottom, with a 2 pi being right there, those two things are going to cancel out, and you'll be left with just theta times radius. Okay? And so that would be arc length when we're living in the land of radians. The arc length is equal to just theta times radius. Now, I'll be honest, I mean, this is the formula your book gives you, so I want to make sure you have it. I very rarely use this formula. I almost always just go back to this because this makes sense to me. This requires me to memorize. Okay, but I want to make sure you have all these formulas in front of you. A similar thing happens here with sector area if we're working in terms of pi. If I do theta over 2 pi, and then I multiply by pi r squared, the 2 doesn't cancel this time, but the pi's do. And so you end up with this sector area equals theta over 2 times r squared. Okay? Again, I think this is harder to remember than this, and I typically just, as I'm working through the problem, know to cancel those pi's out. But I just want you to recognize the formulas that you're going to see in your textbook. This one might actually be written as 1/2 times theta times r squared. I can't remember if your book writes it with a 1/2 or as theta over 2. Either way, it's a more complicated formula to remember, although technically it's been simplified from the original. If you're living in the land of degrees, there's really no shortcuts because there's nothing with degrees that's going to cancel over here. So in the land of degrees, we always just do theta out of 360 times 2 pi r. This right here, just so you know, 2 pi r is also the same thing as pi times diameter. So if the question is asking, if the question provides you a diameter, you could plug that in instead of 2r. So that's a little shortcut you could take. And then sector area, same thing. Theta over 360 times pi r squared. So this is kind of the basis. These are the technical formulas, but in general, this is the strategy that we're using every single time. Fraction of the circumference, fraction of the area. And this is where I typically tend to fall back to when I'm approaching one of these problems. Okay? All right, so let's try some examples. Oh, there's my examples. Oh, I only made you do 2 examples. That's nice of me. Okay, arc length and sector area of a circle with a radius of 8 and a central angle with a measure of 3 pi over 4. So let's start with arc length. So like I said, I always start with this fraction. I know it's theta over, and if I look at my angle, it's being measured in radians. So my whole circle is 2 pi times, and then I'm looking for arc length, so I'm doing 2 times pi times radius. That's my circumference. Okay, I should probably mark that. That's what this is doing, is this is the circumference of the circle. Okay, so when I start plugging things in, my angle, my theta, that's theta, is 3 pi over 4. And this is going to look weird for a minute. Over 2 pi. So this is really taking the fraction of the circle, right? This is saying that I have this much out of 2 pi that is being defined by this sector. And then times 2 times pi times my radius of 8. So now from here, I'm going to go ahead and cross out those 2 pi's. I know that's what's going to happen. I'm left with 3 pi over 4 times 8. And this is where we check and see how good you are with the fractions. I would not jump to putting this into your calculator. If you really had to, you could do the fraction times the 8 in your calculator. Leave the pi out of it because your answer is just going to have a pi in it. So this is really 3 times 8, which is 24 pi over 4. All I did there was think of this as 8 over 1. And then 24 pi over 4 is equivalent to 6 pi. And this would be your final answer. This is the length of the arc defined by that angle. Okay. Let's do the sector area, and then I'm going to draw a picture of what this circle would look like so you can get an idea visually of how these numbers work together. So for sector area, I'm doing theta out of 2 pi, because my whole circle is 2 pi, times pi r squared. So I'm still using that theta of 3 pi over 4. Really, I'm using the same numbers for everything. The only thing that's changed is now this thing here really represents area of the circle, not circumference anymore. So 3 pi over 4 over 2 pi times, and then pi times 8 squared. Okay, and I should point out, I mean, back here I went ahead and crossed out this 2 pi with this 2 pi because that's just what we had done before. You technically have like 3 pi's going on here. And so this one or this one of these is going to cancel with that 2 pi down there. This is on the bottom of a fraction. These are both in the numerator of a fraction. So one of these two is going to cancel. For consistency, I usually just cancel this one here with this one. Okay. And then when I'm dividing a fraction by 2, so I'm kind of stepping off to the side here, and I wouldn't expect you to normally write this down, but I want you to see what I'm doing here. I'm ignoring the pi for right now. I'm just thinking about what would 3/4 divided by 2 equal. When you're dividing a fraction by something, you can really just combine the denominators because remember, this is already a division problem. We kind of talked about this in the last chapter. So my 3/4 divided by 2 would really become 3/8. So now I have 3 pi over 8 times 64. That's the 8 squared. Okay. And then I'm doing 3/8 times 64. And if you have to use a calculator for that, that's fine. I'm going to talk you through my mental math here. I'm really going to do 64 divided by 8 is 8. And then 8 times 3 is 24. So that works out to be 24 pi as my answer. Notice that I did all of these calculations without touching the pi. I leave the pi alone. I crunch all the numbers with all the fractions and everything. And then I just stick the pi back in my answer. So just so you, and I don't know that you have to do this with every single one of these problems, but I want to give you a visual of what this circle would look like that we just drew. Okay. Tells me I have a radius of 8 and an angle of 3 pi over 4. We're going to talk radians eventually, but 3 pi over 4 is really equivalent to like 135 degrees. 2 pi over 4 is like pi over 2, which is 90. So 3 pi over 2 is over here somewhere. And like I said, don't worry, that's coming in the next lesson. Okay, so the circumference of the entire circle would be 2 times pi times the radius of 8, which would be 16 pi. And so what we're saying up here with our answer of 6 pi is that this length would be 6 pi out of a total distance of 16 pi. Okay, which if you think about it fraction-wise, I mean, 6 pi over 16 pi would be the same thing as like 3/8. So what I have kind of sectioned off right here is 3/8 of the circle. And hopefully that makes sense to you visually. Okay, 3/8 of the circle, 4/8 of the circle would be half of the circle. So I think 3/8 looks reasonable here. Okay. You could also think about it as like, let's actually divide the circle into 8 pieces. So 1, 2, think about cutting a pizza here. And so what I have here in my sector is 1, 2, 3 out of the 8 pieces. So 3/8 of my circumference would be represented by 6 pi. Similarly with 24 pi, so the area of my circle, the way it's written right now, would be pi times my radius squared. So that's 64 pi. We had that up here somewhere. Well, we had a 64 that was going to be multiplied by a pi. And notice we were doing 3/8 of 64. So same deal here. If I did 24 pi out of 64 pi, because we came up with an area of 24 up here, cross out your pi's and reduce this. This would also reduce to 3/8 of the circle. So again, that math that I just did down there was more to justify why these answers are correct. It's not something that you would have to do with every problem, but I just wanted you to connect visually with what was actually going on here. Okay, example 2 here, I'm fairly certain is going to make you do some backwards work, and those ones get a little bit trickier. So a sector in its circle with a radius of 3 has an area of 2 pi. What is the measure of the angle? Okay, so backtracking here, if I'm talking about sector area, and this one, I mean, it's asking you to find the central angle. It's not telling you whether you have to work in degrees or radians. I think I'm going to work in degrees just because we already did one in radians. But then maybe when I'm done, I'll backtrack and show you how to do it in radians as well, because I know that you'll encounter that on your assignment. So let's see. We know the formula. That's what I'm starting with. Theta over 360 times pi r squared. And now I'm going to fill in the pieces that I know. This time I know the sector area is 2 pi. So I'm filling in 2 pi here. I don't know theta. Theta is the thing that's missing, so I'm leaving that as a variable. And then multiplying by pi times my radius of 3 squared. Okay, I see lots of different ways that we could approach this one. So if you choose to do something different, that's fine. The first thing I notice is I've got pi's on either side of the equation. So technically what I'm doing here is dividing both sides by pi, but I'm just getting rid of those pi's, okay? I am also going to take this 3 squared, which is really a 9, and I'm just going to incorporate it into this fraction. So now what my equation looks like is this. 2 equals 9 theta over 360. And then from here, theta is like an x, right? It's like my variable that I'm trying to solve for. So if this was an x, to get rid of this fraction, I would probably multiply by a reciprocal. I think that's the quickest way to go. You could go through and like multiply by 360 on both sides and then divide by 9, but you can get rid of the whole thing in one shot by multiplying by 360 over 9. Multiply by 360 over 9. And let's see, so on this side, whoops, didn't mean to cross that off. Really, it crosses off with that. On this side, let's see, 360 over 9, doing some mental math here. You could do this in your calculator. 360 divided by 9 should be 40. So 40 times 2 gives me 80. So 80 degrees for theta. Okay. And so if you went and worked backwards here, you should find that with an 80-degree angle, you end up with an area of 2 pi for your sector out of whatever the area of the entire circle would be, okay? Which you don't have to calculate, but again, if you just wanted a visual, you could do that. Okay, let me run through that example again with working in radians, because I do think some of the pi's and fractions and stuff get a little dicey there. So let's do that one again in radians, just so you can see how to do it both ways. So I'm going to start the same way. I'm going to start with sector area, except this time I'm going to set it up as theta over 2 pi times pi r squared. I would recommend always writing out this formula first before you start. And so then I'm filling in, just like before, I know my sector area is 2 pi equals theta over 2 pi times pi times, oh, not 9 squared, sorry, 3 squared, which is 9. Okay, just want you to see where I'm putting the numbers. So the only thing that's different so far is I'm using a 2 pi instead of a 360. Okay. This is where the pi's can get confusing. Remember how back here we were able to cancel out these 2 pi's? I can still do that. I can cancel out these 2 pi's, or I can cancel out these 2 pi's. I just can't cancel both, right? And I would say I want to get rid of the pi's that are on either side. I'd love for this side to just be a solid whole number. So just like we did before, I'm going to get rid of this pi and this pi, but now this pi is still here, okay? And just like before, I'm going to take the 3 squared and kind of incorporate it into this fraction. So now I have 2 equals 9 theta over 2 pi. And we got rid of our other pi, so that's it. And then I'm going to multiply by a reciprocal like I did before. And I'm not touching the pi button in my calculator here. I'm just multiplying by 2 pi over 9 and multiplying by 2 pi over 9. Okay, so these cancel. And here, again, I'm ignoring the pi. 2 times 2 is 4 over 9. So this would give me 4 pi over 9 for theta. Okay. And if you check, and again, I know we haven't done these conversions yet, we're going to get there, but in radians, 1 pi is equivalent to 180 degrees. Maybe you remember that. So you can check and see what this would be in degrees by doing 4 times 180 divided by 9. And you'll see that that's equivalent to the 80 degrees that we got up here. So with this one, I followed all of the same steps. Okay, don't let this 2 pi throw you off. It just means your answer is going to have a pi in it, but it's supposed to because we're looking for a radian angle measure. We didn't have a pi back here because we were looking for a degree angle measure. If the question doesn't specify, I would take your answer either way. So if you like the degrees better, go for the degrees. But if it does specify that you have to do it in radians, this is the process you would work through. Okay. You're also going to have some problems like this where they give you the central angle, but then you have to solve for like the radius or something too. And again, the process is the same. You lay it all out in the formula and then just do some algebra. I would just not ever put the pi in your calculator. Do all the other calculations and just leave the pi sitting there in your answer. Okay, hopefully that was enough on this one. You've got a homework assignment that goes along with this, and then we will talk about that some more next time I see you in class. All right, have a great day.